Hi, I'm Kelly. Have you ever wondered what is so special about colorants like pigments and dyes that makes them colored? Today I'm gonna talk about chemistry of colors. So what makes things colored? When molecules or electrons move from the ground state to the excited state, they absorb energy. And the colored substance absorbs light in the visible spectrum. So, what causes this? It could be due to various reasons, for example, vibration and rotation of atoms or ligand field effect. And in this presentation, I'm gonna focus on conjugation of organic compounds and charge transfer. Before we move on to our main topic, conjugation, we should first explain what happens when p orbitals interact in the formation of pi bonds. So here is the molecule ethene with the double bond you can see here. And in a double bond, you can find two types of bonding, the sigma bond and the pi bond. So we're gonna focus on the pi bond here. Pi bonds are formed by p orbital overlapping side to side, like this. And orbitals are regions where you can find electrons, and p orbitals are one kind of orbitals which have a specific shape, and the blue ones here you can see are p orbitals. In this example, we have two p orbitals overlapping, and the two atomic orbitals will combine to form two molecular orbitals because the number of atomic orbitals we put in will be the number of molecular orbitals that we get. Diagram on the right is the orbital energy level diagram, which shows the energy level of orbitals. The ones in the middle are MO, which are formed after the interaction, while the ones on the sides are original atomic orbitals. But why are there two molecular orbitals of different energy levels formed? This is because electrons have wave properties and atomic orbitals are wave functions. So they combine in the same wave that waves combine, which are in two ways, constructive or destructive. In the constructive case, they combine in phase like this, and they will add together and form a larger wave, while in the destructive case, they combine out of phase. That means they'll cancel out each other. And now we have two pi electrons and we need to fill it into the orbitals. We would like the electrons to fill in orbitals with lower energy first to maintain stability. So the two pi electrons will go into this bonding molecular orbital instead of the anti-bonding. We will call this the HOMO, which stands for the highest occupied molecular orbital, and this the LUMO, the lowest unoccupied molecular orbital. Now we'll move on to conjugated pi systems. Conjugation takes place when there is alternating single and double bonds, like here in this molecule, the 1,3-butadiene, we have these alternating single and double bonds. And instead of two p orbitals overlapping, we have four p orbitals overlapping. And as a result, four MO will be formed. And half of the MO is bonding MO, while half is anti-bonding MO, which are of higher energy. So the pictures here show how what combinations can be formed between the overlapping of p orbitals in phase or out of phase. Same colors mean they can combine in phase while different colors will not, so a node will form between them. And again, we have the HOMO and the LUMO here. When a molecule absorbs energy, its electrons can be promoted from its ground state to the excited state, which means from the HOMO to the LUMO. And the energy difference between the HOMO and the LUMO corresponds to a certain wavelength of light, which the compound can absorb. And as we have the famous equation, the Planck's relation, E equals hf, and we know that speed of light c equals f lambda. As we combine the two equations, we get E equals hc over lambda, while the lambda is the wavelength. If we increase the energy, the wavelength will decrease, and if we decrease the energy, the wavelength will increase. And as we see in the diagram on the right, the more conjugated the system is, that means the more alternating single and double bonds we have, the smaller the gap between HOMO and LUMO, which means the larger the wavelength of light the compound can absorb. For ethene and butadiene, the waves absorbed are still in the ultraviolet section of the electromagnetic spectrum, which makes them appear as colorless. But as the conjugate system gets extended and reach octatetraene, it starts to absorb visible light, which is what we want. Here are some examples of pigments. This is lycopene with the conjugate system here, and it's the red pigment in tomatoes. It absorbs blue to green light, but it appears at red, which is the opposite of blue and green in this color wheel. This color wheel can help us identify the color of the molecule according to the light it absorbed, which is the opposite of it. Another example is the beta carotene. It's the orange pigment in carrots, and it absorbs blue light and appears as the color opposite to it, which is orange. And this is chlorophyll, which is the green pigment in plants. It contains this cyclic conjugated system and which absorbs longer waves. Therefore, it appears as green. In the nature, blue and green pigments are rare because they rely on more conjugate system. And now as we understand how conjugate system is related to colors of molecules, it's not hard to understand how chemical bleaching works. Bleach that we find at home are diluted solutions of sodium hypochlorite, which is NaClO. It is used to whiten clothes and remove stains or as a disinfectant. It works by reacting with the pi bonds responsible for the color of these molecules and breaking down the conjugated system. The NaClO sodium hypochlorite contains the Na plus ion and the hypochlorite anion, which is the ClO minus. And in the hypochlorite anion, the oxygen atom is more electronegative than the chlorine atom. Therefore, chlorine atom becomes partial positive and the oxygen becomes partial negative. Therefore, it can react with the pi bonds in the conjugate system by electrophilic addition reaction. And this is how the conjugated system is broken down. Now I'll talk about dyes. Dyes contains groups called chromophores, which are the color-bearing groups. That means it's responsible for its color. It contains conjugate systems like benzene rings and alternating single and double bonds between carbon atoms. And there's also this azo group. It's one of the most common chromophore found in dyes. These chromophore groups are usually conjugate systems themselves or located in a conjugate system. For example, this brown dye here, it has a conjugate system formed by benzene rings and azo groups, and this whole chunk is the chromophore. And apart from chromophores, we have oxochromes. Oxochromes are substituents that are added to the chromophores that fine-tunes the color by shifting the absorption band to the targeted wavelength. It can be both electron donating groups or acceptor groups, as you can see here. And for example, in this acid brown dye here, there are NH2 amine groups added here, here, and here. But how do oxochromes work? How do they shift the absorption band to a longer wavelength? It's usually done by extending the conjugate system by direct conjugation or in other ways. So let's have a look at the example of the crystal violet dye. The central part with the many alternating single and double bonds is the chromophore, while these three parts are the oxychromes. The two amine groups act as the electron donor, and this group here acts as the electron acceptor. Another concept of mesomeric effect will be involved here, so let me briefly introduce it. It occurs when pi electrons move away or towards a substituent group in a conjugated system. In this case, mesomeric effect occurs. As a result, the donating group pump electrons into the conjugate system. Another way of looking at this is to notice that the nitrogen in this amine group has lone pair of electrons. The lone pair is located in a non-bonding orbital, which can strongly interact with the orbitals in the conjugated system. This also provides a non-bonding orbital for N to pi star transition, while N stands for a non-bonding orbital and pi star is anti-bonding pi orbital. And in the examples at the start of this presentation, transitions from HOMO to LUMO are all pi to pi star transition. But this N to pi star transition gives absorption of even longer wavelengths, since the energy difference is smaller. Another thing to notice here is that these two diagrams are of the same molecule but with a little difference. They have the same arrangement of atomic nuclei but different distribution of electrons. The curly arrow shows the movement of electrons in the molecule, and these structures are called resonance structures. Because of the delocalization of electrons in the molecule, the structure of the molecule cannot be shown with only one diagram. Therefore, these resonance structures are used to show how electrons are delocalized. The real molecule is a hybrid of these resonance structures since the delocalized electrons are moving all the time. And resonance and mesomeric effect are basically the same thing, as they're both used to describe the delocalization of pi electrons in the conjugate system. And the more resonance structure, the stronger the mesomeric effect, and which stabilize the molecule and lead to a smaller HOMO-LUMO gap. And hence the absorption of light will shift to a longer wavelength. In the last part, I will be talking about the blue color of the blue sapphire. Blue sapphire is one of the two varieties of corundum, which is aluminium oxide, Al2O3. When talking about aluminium oxide, you might think that it's an ionic compound, but actually the bonding in corundum has a sufficiently large covalent component, so a single crystal of corundum is not composed of individual ions or molecules, but consists of a rigid framework structure, which is drawn here. Usually these two atoms would be aluminium, which is surrounded by 6 oxygen atoms in the form of a distorted octahedron. But why are these two not aluminium atoms is because corundum contain less than 0.1% of both iron and titanium oxides. Corundum with only titanium as impurities is colorless, and with only iron is pale yellow, but with both of them it gives a blue color. This is because there is enough overlap between the d orbitals of the Fe2+ and the Ti4+ ions. This causes the intervalence charge transfer to occur and results in the temporary change in oxidation states of both ions. Fe2+ converts into Fe3+, while the energy of this new combination is higher than the original one. As a result, light of all colors but blue and violet blue will be absorbed, and sapphire will appear as blue color. And this is the end of the video. Thank you for listening.